Hello, everyone. Today we're going to be going over through EE370 for the second midterm. So we're going to be doing a review. So we're going to continue where we left off. And basically, we're going to start with the system response. And so when we have our transfer function, g of s, it's equal to two polynomials. There's one in the numerator and one in the denominator. And so the poles are determined by what makes the denominator equal to 0. So the poles are values of s that make d of s equal 0. And in the numerator here, these are the zeros. And so are the values of s that make n of s equal 0. And so when we're plotting a lot of times in our transfer function onto a pole 0 plot, what we have is we have specifically the following graph. This is the S plane where we have our sigma in our j omega axis. We plot the poles in zeros. The poles will be indicated by an X, where the zeros will be indicated by an open circle. And so this is the common pole 0 plot we'll be working with. So let's do an example. So for our example, we're going to be given the transfer function g of s is equal to s plus 2 all over s minus 5. And we want to plot the poles and zeros of this. So in order to do that, we're going to draw our pole 0 plot, and we're going to get the following. So on our pole 0 plot here, we're going to have, of course, our j omega, our sigma, and what we notice is the value of s that makes the numerator equal 0 is -2. So that's our 0 at -2 here. And then the value of s that makes our denominator equal to 0 is going to be +5. So over here at +5, that's where we're going to have a pole. And so that's just one example. Now let's do another one that is a little more complicated. It's going to be g of s is equal to 2 all over s squared plus 2s plus 2. And so looking at this, we have a quadratic in the denominator. So we need to find the roots of this quadratic equation. So we're going to use the formula where we're going to have s equals and then -b plus minus square root b squared minus 4ac all over 2a. And when we solve this quadratic equation, we're going to simplify. So this would be 4 minus 8, so it would be -4, then all over 2. And so simplifying even further, we're going to get -2 plus minus j2 all over 2, which is equal to, and then -1, and then plus minus j. And so here, what we can do in order to rewrite this is it's going to be 2 all over, and then it's going to be s minus, and then here we have -1 plus j for the first one, and then we have s minus, and then it's going to be -1 minus j. And so just simplifying that denominator here for g of s, I'm going to write it down here. It's going to be 2 all over, and then it's going to be s plus 1 minus j. And then here we're going to have s plus 1 plus j. Okay. And now we're going to plot this specifically on our pole 0 plot. And what we're going to see is I'm going to have -1. Then here I'm going to have my j and -j. So the value of s notice in the numerator, we have no s, so we're going to have no zeros. But here in denominator, we have 2 of our s terms. And for the first one here, it's going to equal 0 when s is equal to -1 plus j. So at -1 plus j, that's the first pole. And then here, to make this term equal 0, s is going to equal -1 minus j. And so that would be the example of our pole 0 plot in order to make this denominator equal to 0. Okay, now that we have that, we're going to go to the next part, which is focusing on first order systems. Okay, so first order systems, what are they? A first order system can be represented by g of s is equal to k all over tau s plus 1, or, and then here we're going to have g of s is equal to b over s plus a. And so how can we go from this form over to this form? We'll divide everything in this format here by tau. And so you're just going to get the coefficient of, you're just going to get the coefficient of 1 in front of the s term, no longer tau. So then it will match the other form. So what you're going to see here is basically when we do this simplification, you're going to see that if we're trying to go from this form as well to get the form over here, what we can do is we can divide by a, because isn't this one to this one the only difference here? Here we have a 1. If we divide this one by a, you get b over a divided by s over a plus 1. So that would be another way you could convert over to this one. So you can interchange between the two forms. So I'm just going to illustrate that if you took this one here and you did b divided by a all over s divided by a plus 1, if you set, so let k equal b over a and tau equal 1 over a, you're going to get k over tau plus 1. Tau s, sorry, plus 1. And so that's your g of s. So that's how you would go from this format. You can convert it over to this format. And you can do it vice versa. You can convert from this one over this one. But notice a lot of times in industry, they use this format. And so what we like to do is we like to call this tau here the time constant. So this is known as our time constant. And k here is known as the final value. And so that is an important note to take into account here. We often represent it in this form because it's easier to plot the poles in compared to this one, but you can convert from this one over here. So make sure you know your first order systems, the two types of formats that they can come in, and know that if you just you can convert from this form over to the other using that simple algebra. And now that we saw that, what we're going to do here is we're going to try and have a few definitions with first order systems. So when we have a first order system, the unit step response is given as follows. It goes upwards like this. So this is our unit step response for a first order system. So the important thing to notice here is that it reaches tau at about 63%. So I'm going to mark this. It's about 0.63 of the final value. And so this would be your final value, of course, where it's finally going to go to. Your rise time is going to be about 2.2 times tau. So the rise time here, a lot of times in books, it's calculated from 0.1. So here is about 0.1 to about 0.9 of the final value. So the rise time would be from this slot here, from 0.1. And if we look at where it intercepts 0.9, so it would be right here, that time interval, the rise time, how it goes from 0.1 to 0.9, the time in between, in order to, of course, rise. That makes sense why the name's there. And then the other one is going to be your settling time. So the settling time defined here is to reach and stay within 2% of the final value. So of course that would be at around 0.98 here we would have. So our settling time starts from 0 and goes to about 0.98. So that's the settling time. So to stay within 2% of the final value. So it goes up here to 0.98 of that final value. So we need to define these so we have them. So tau is equal to 63% of final value. The rise time is approximately 2.2 times tau. And the settling time, it is 98% of the final value, the amount of time. It's approximately, though, 4 tau. And so what we're going to do is for the following one, which is g of s, is equal to 50 all over s plus 50. For this example, we need to determine tau, t of s, which is the settling time, and rise time of the unit step response. Well, we know for the unit step response of a first order system, it's given by the following. So our final value from here, notice that they gave this equation in the format of b over s plus a. And remember how we said that you can go from this format and you can calculate it so you get k all over tau of s plus 1. And what we're going to do here is recall, if we're going to put it into this format, we're going to change it. We divide everything by a, and a here's 50. So what we're going to do is we're going to have 50 divided by 50 all over, and then this would be 1 divided by 50 times s plus 1. And so that is just equivalent to 1 over 50 s plus 1. And so what we're going to see is our tau here, tau equals 1 divided by 50, which is equal to 0.02 seconds. And then our next one is the settling time, which is approximately 4 times tau. And that's going to be 4 times 0.02, so that's 0.08 seconds. And then the rise time, which is approximately 2.2 times tau, which is going to be 2.2 times 0.02, which is going to be 0.044 seconds. So that's how we would calculate tau, the settling time, and the rise time for the unit step response, because we know the unit step response, and we know specifically for the unit step response of a first order system, tau is defined as 63% of the final value. We have our settling time and rise time. In using the format here to convert from the generic format of plotting the poles and zeros to the format that gives us the final value all over tau, we can easily find the tau value and then from that derive the settling time and rise time. Notice that the final value is 1, which makes sense up here. K is 1 because it's the unit step response. So of course it's going to hit 1 at its endpoint. Okay, the next one that we're going to do is we're going to look at a second order system. And so a system which has two poles is called a second order system. Notice how we've been dealing with the case where we've only had one pole in our examples here. We only had one to begin with, s plus 50, so the pole's at negative 50. But here when we have two poles, that's when we call it a second order system. So one example of two poles would be G of S is equal to, and then 3 all over S plus 1 times S plus 3. The poles here, one would be at -1, one would be at -3. So one of our poles would be -1, the other -3. And so that's why we have two poles, so it's a second order system. So when you'd plot it, of course, you would have at -1 and -3. That would be your pole 0 plot. Okay, so what's the general form of a second order system? Just like the first order system, we have to define a few of the basics. So for a second order system, it's going to have the following equation. We're going to have G of S is equal to omega n squared. So this is the natural frequency squared all over S squared plus 2 zeta omega n S plus omega n squared. And so defining these terms, our omega n is the natural frequency. Zeta here is our damping ratio. So this one is the damping ratio. And then what we're going to notice is that these two, zeta times omega n here, this is referred to as, a lot of times we use sigma d to represent it. That just refers to damping. And then we have the next one, which is, it's not defined in here, but you should know it with second order systems, is omega d, which is equal to omega n in the square root. And then under square root, we have 1 minus zeta squared. And this is known as the damped natural frequency. And so what we're going to see from this is when we do our poles, you're going to notice the poles are going to come in the form S1, 2, because remember, there's two poles in a second order system. And then it's going to be negative zeta omega n plus minus j omega n, and then the square root of 1 minus zeta squared. But we like to simplify that, so that's why we use the minus, and then we use the sigma d plus minus j omega d. And so that's why we use these two, where we just combined zeta omega n under the sigma d, and then we combined omega n square root 1 minus zeta squared as omega d. And so this is just a simplification for what the poles will be represented as. Or there's 1/3 way to represent them, which would be omega n, and then it's going to be pi plus minus theta. And this is where theta is equal to cosine inverse of zeta. So that's important to know when you solve for your poles of a second order system, that they're given by the following equation here. And this angle will come in handy. We'll see later on. It can also be represented by the following forms. Okay, now that we talked about what a second order system is and how it has two poles, what we're going to see specifically is let's look at the plot of a second order system and how we're going to make it. And so the plot of a second order system is a little bit different than the first order. What you're going to see here is within your plot, you have the j omega still, and you have your sigma, of course, on your x-axis. What's going to be a little different, though, is you're going to be able to tell that when you have your two pole locations, so say our poles are here and here. Sorry, those aren't aligned as well, but they are complex poles, so they come in pairs. They should be directly on top of each other. And when we draw the line here from the origin to our pole, this is going to be the length of omega n, which makes sense here, omega n, the length of omega n. And then our angle here, what we're going to see is when you normally take the angle, the reason why we have to do this pi and then plus or minus theta is because our theta is the angle right here when we're calculating the distance. So this here is actually pi minus theta. So that's why they write it in this format, pi minus plus or minus theta, depending on where it's located, your pole. Then what you're going to have for your y, so this is the y, the distance from your real axis. This is going to be known as your j omega n, and then it's going to be 1 minus your zeta squared, or simply as j omega d. So you'll see your imaginary axis, it would be in terms of j omega d, where how much distance you go along the x-axis. So that would be here. How much is your distance here along the x-axis? That's going to be represented as negative zeta omega n, which is negative, and then sigma d. It can be represented as. So you'll often see it's j omega d for our y-axis, and it's going to be negative sigma d for your x-axis, because of course this is in the negative direction. And so a lot of times people might forget that you can easily calculate your zeta value from your angle. So remember, zeta is equal to the cosine inverse, theta is equal cosine inverse of zeta. And so the nice part about this is if you know your zeta, you can easily calculate your theta value in order to have a good interpretation behind it. But you can also, if you know cosine of theta, say you know your theta, it's equal to zeta omega n all over omega n, your natural frequency. And so that comes in handy as well. So let's now look a little bit into the details of our second order system and what the zeta value, how it represents the damping ratio. And so we're going to begin, we're going to look at 4 types. So here's our pole 0 plot, and we're going to look at 4 different conditions here. Okay, so for the first condition, we're going to have our poles, and they're going to be on the j omega axis. For the next condition, we're going to have our poles, but they're going to be a little bit to the left of the j omega axis. And then for next one, we're going to have our poles here repeated. And then for next one, we're going to have our poles, but they are distinct from each other. And so what we're going to see here is our zeta value. For the first one, zeta is equal to 0. And so remember that's the damping ratio. So here we're going to notice for our step response, what it's going to look like when zeta is equal to 0, so you can build some intuition, is your plot. If you're along the j omega axis, this causes damping. And so when your damping ratio is equal to 0, you're going to have your oscillatory waveform. And so for the next one, you're going to notice in this system, so this would be an undamped system. And then for when we have zeta, and it's going to be between 0 and 1, what we're going to see for our output graph is it's going to be an underdamped system. So you'll notice at the beginning, there's sort of a little bit of the oscillatory part, but it dies out. This will be our underdamped. And then for our next part where we have repeated poles, and then this is on the real axis, what we're going to notice is that our zeta is equal to 1. And so then we're going to have basically none of that damping. It's going to go pretty much up. It's our critically damped case. And so our critically damped case, we're going to notice that it goes upwards and just flattens. And then when we have them distinct from one another, not repeated, this is when zeta is greater than 1. And so what we're going to see for our graph is that for the overdamped system here, it's going to go upwards just like that. And so we notice the different responses we're going to get. If we have our poles on the imaginary axis, it's going to look more oscillatory. And as we move our poles closer, it's going to have less of the oscillatory shape. And then here it's for our overdamped system, we can see it is pretty much following what we're going to have. Like if we had a unit step, it is the closest to it. So that's what we'll see as we progress throughout this class. So the big part here is just seeing how zeta, that damping ratio, affects your system. And so we're going to try and do an example with this. So what we want to do is we want to find the unit step response of this system. And so what we have here within our system is we have the block diagram where we have 9 over s squared plus 9. And then we're going to have an input and we're going to have an output from the system. So this is our system G of S. And our input is going to be, because it says unit step response, the input's a unit step. So 1 over S, that's the Laplace transform. Then we're going to have our output, which is C of S. So we have to find that response. So we have to find the output. And so what we're going to have is we're going to have, remember, C of S is equal to R of S times G of S. So this would be our 1 over S multiplied by 9 over S squared plus 9. And so what you're going to get for your C of S, basically, when you solve for this, you're going to see that you're going to have to do a little bit of partial fraction expansion. Reason being is because you have the multiplication of the two, but you're going to get an S cubed term. And so it's going to be too great. You can't use a quadratic equation on an S cubed. So you're going to have to do A all over S plus B over S squared plus 9. And what you're going to do then in order to solve for this, we'll do this example, and then we'll look at our other ones. Remember, this is going to be B, and then you have one less than, so it's going to be B S, and then plus C, I believe that's how it works. So you would then, if we need to solve for our A, we would say that S squared plus 9 times C of S, and then evaluated at, and then it'd be what's going to make this equal to 0. And so then it would be S equals, I think he would just provide this to you because this one would be a little complicated because S squared here would have to equal -9. And so you would have to do a process within there, but he gave you the partial fraction expansion because it was a little complicated as -S over S plus 9 times 1 over S after you would solve for this. And so what you would do, so he gave you what A would be and what B would be and then C. And so this would be your actual response after that partial fraction expansion. And so now, given this, you would have to then convert this over into the time domain to see its response, of course, when you plot it in the time domain. And what you're going to see from the following two is, remember, this is going to be your unit step. So this would be, oh, sorry, I forgot the plus sign. This would be the unit step when you convert it over using the inverse Laplace transform. Let me see if I have the table here that I can bring up. This one would be UT for sure. And then this one here, we have a negative sign in front. Oh, sorry, I forgot to write the S squared here. We have a negative sign. So of course we're going to have a negative sign. And then if you match this up on the table, this would be your cosine. And then it would be 3t and then u of t. And so this would be your C of t. And so what you have to do from here is you're going to take out the UT common to both terms. So for your answer, you'll get 1 minus cosine of 3t u of t. And that will be your response in the time domain. And so when you graph that, you're going to see a cosine waveform. And that's pretty much, notice that there's no middle factor here, the S term, like we talked about with our response. So this must have been equal to 0 because it was only S squared plus omega n squared. There was no middle S term in our system function here. And so that's why we have an oscillatory part. So that's what we saw because the damping ratio was equal to 0. So that makes sense for our answer. And so from this, you can dissect. The big thing is notice from this transfer function that your damping ratio was equal to 0 and that your natural frequency is the square root of the constant. So the square root of 9 is 3. And so those are just some observations you'll be able to make from that. And now we're going to do another example where you need to find the unit step response for the system. And we're given, remember, our input then must be the unit step. So take Laplace transform, that's 1 over S. And that's going to pass through our system, which is going to be given here by the block diagram of 9 over S squared plus 2S plus 9. And then that's going to create our output C of S. So this is our G of S, of course, our system. And what we're going to see is, if we're to solve for this, remember, omega n is the square root of the constant. So omega n must equal 3. And then we have in here, recall, from our second order system, this is 2 zeta omega ns. So right here, what we're going to see is that we're going to have 2 zeta omega n s is going to equal to s. And so what we can tell from this basically is, of course, our divided by 2, we're going to get our damping ratio here. And what we're going to see, plug in what you know. So we're going to see zeta omega n is going to equal 1 when we divide by 2s on both sides, because this one will cancel with this one. And then omega n we know is 3 because it was the square root of the constant here. So it's going to be zeta times 3 is equal to 1. So zeta is equal to 1/3. Okay, so we got zeta. And notice that zeta then falls in between 0 and 1. And that's an underdamped system. So that's what we're going to see is this will be underdamped. In the previous case of what we notice is, remember, that was our underdamped. The first one was the undamped system up here. So this one was undamped because zeta was equal to 0. So this one was undamped. Then we had our underdamped. For underdamped, what we're going to see here is when we calculate the output C of S, it's going to be equal to the input multiplied by the transfer function. And so our input is 1 over S multiplied by our transfer function, which is going to be 9 over S squared plus 2S plus 9. Notice that this is going to give you an S cubed term. And so then we're going to use partial fraction expansion so we can write this. When you use the partial fraction expansion, you're going to get the result of negative S minus 2 over S squared plus 2S plus 9, and then plus 1 over S. And so then when you have to convert this into the time domain, what's going to happen? How are you going to be able to do that? What you're going to see specifically in the table, well, of course, this one's going to be your U of t. But when you take the inverse Laplace transform of this one, you're going to get the following. It's going to be minus, that minus will come out, and then it's going to be e to the negative t, and then it's going to be cosine, then square root 8t plus square root 8 all over 8 sine, and then square root 8t, and then this one, so ut. This one over here was just u of t, so I'll just put the u of t over here. You would just use the inverse Laplace transform table in order to convert this into a time domain. That's what we did here. And then now we could take out that ut common to both terms. So you're going to get 1 minus e negative t, and then cosine square root 8t plus square root 8 over 8 sine square root 8, and then t. And this is going to be all multiplied by u of t. So that would be your answer. And so you are going to notice a little bit of oscillatory part when we draw out the waveform, when you look at this in MATLAB, because of that damping ratio. So it's going to look a little like that. And so this is going to be your plot for the unit step response. And so now that we saw that, basically, the next ones, I'm just going to identify what you'll notice based on the system transfer function, because based on that transfer function that it's going to go through, that's going to tell you how much of your damping ratio is and what your response should look like. And I think that's the big thing he was trying to get at here within these examples, is you want to know what your response is going to be. So for this one, they gave you they wanted to determine the unit step response of the system. And when you have to determine the unit step response of the system, R of S is equal to 1 over S. And then it went through, and then we had here as our transfer function 9 over S squared plus 6S plus 9. And then we got our output C of S. Big thing here is now I'm just going to analyze omega n is equal to the square root of the constant term in the denominator. So that's 3. And then we're going to see this part right here is 2 zeta omega n s is equal to 6s. What you're going to do is you're going to plug in and simplify. So what we're going to see is 2 zeta omega n, we know is 3 times s is equal to 6s. Well, this now will become 2 times 3 is 6s times zeta is equal to 6s. Divide, you're going to get zeta is equal to 1. So when you have zeta equal to 1, what your response will be, as we had here, is critically damped. So this is what it should look like when you solve for it. So this is the critically damped case. And then the final one, what you're going to do for this example that they gave you is when they give you R of S is equal to 1 over S, and it goes through the system transfer function, which you're going to have here as 9 over S squared plus 9S plus 9. And it's going to be C of S here. When you're analyzing in order to determine the response of the system, what we're going to see is omega n is equal to 3. And then our 2 zeta omega n s is going to equal 9s. Plugging in for omega n, we're going to get the result. What do we see here? It's going to be 6s zeta is equal to 9s. And divide by 6s, you're going to get 3 divided by 2. And so we're going to notice that this response will be over damped, and these are what our poles will look like. So that's just the different types of scenarios that you might be asked to identify. If you were given the plot of the graph, you could determine, oh, yeah, it should look over damped, or oh, it should look critically damped. So it's good in order to identify the omega n and how much of the damping ratio then you can use from that omega n value to notice what's the type of response we should be expecting. And so now that we saw that, what we're going to look at is when we have our calculations, we're going to see for underdamped systems, we want to focus a little more on them. So I'm going to make this section just about the underdamped systems. So remember, underdamped was dealing with the oscillatory part we had. Oh, let me see. I think he meant here is, yeah, that is correct. The underdamped, sorry, is dealing with this one, which has the oscillatory part at the beginning, and then it dies out. So when we're looking at underdamped systems in particular, there's some specifications that we want to go over and be familiar with. So within our underdamped system, the plot looks like this, where we have time on the x-axis, and we're going to have our graph. It's going to go the following. And within ours, we'll the overshoot. And so this one overshoots what the response is going to be. You'll notice it goes above all the others. So that's why we call it the overshoot. And so think of our response. It's going to go to 1, of course, the unit step response. So this will be our 1 point. And so what we notice right here is this is what we call the overshoot. And then what we like to say a lot of times is we'll be looking at in the next chapter, but this is our final value that we expect. But we notice that as time goes to infinity, there's a little bit of a difference. So this is known as the steady state error, that there's a little error between the final value and the actual response value as time goes to infinity. It's not exactly at that one value. And then what we're going to see is rise time. So I'm going to define the rise time, which is T of R, of course. It's to go from 0.1 to 0.9 of the final value. And so our rise time, what we're going to see, our 0.9 part would be right around here. This would be about 0.9. Our 0.1 part would be like right around here. So the time that it takes to go from here all the way to 0.9 here, this is known as our rise time. And then our settling time is to reach and stay within 2% of the final value. And so our final value was 1. So here at this specific point, if we're looking at within 2% of 1, we're going to have just a little above 1 and then a little below 1 to stay within 2% of that 1 value. And so the settling time, the first one, when it starts to be within that, we're going to notice that here it no longer escapes. It stays within 2% after this specific threshold. And so that is known as our settling time. And so it's the time in order to stay within 2% of the final value. And so that's the settling time. And so I'll define that here, settling time, which is T of S. That's known as time for response to reach and remain within 2% of the final value, which is 1 in this example. And there is an equation for the settling time, which is equal to 4 over sigma d, which is equal to 4 all over zeta omega n. And so that's what you're going to notice specifically. Remember, sigma d is zeta omega n. That's how much is on your real axis, so you know. So know this formula, make sure you have it. In the peak time is, so I'm going to put that here, peak time is known as TP, and that is to reach the first or maximum peak, the time to reach first peak. And of course, the first peak is at that point where the overshoot occurs. So this would be your peak time up here, your T of P, how long it takes specifically in order to get to this first peak. So this specific time right here, when that occurs. So you would just look right down here. What is that time slot? And so the peak time can be calculated from the following formula, pi over omega d. And then percentage overshoot, they have an equation for it, but let me just make sure. Remember, your rise time is 0.1 to 0.9 of the final value. Your settling time is given by this equation here. Your peak time is given by the equation here, but we were able to identify all those from the graph. Know your settling time is remain within 2%, so that's why it's 4 over, and then zeta omega n. Your peak time is to reach the first peak, so it's pi over omega d. Your percentage overshoot which also is abbreviated as percentage overshoot. This is going to be how much the waveform overshoots the final value. So that is a percentage of the steady state value. So how much is that percentage? Like, does it overshoot the final value by like 20%? Does it overshoot like, so how high does this go? If it went to 1.2, of course, that's 20% more than the final value of 1. And so what we're going to see here is the percentage overshoot has a few equations that defines it. It can be the maximum minus the final, which makes sense, all over the final times 100 to find out how much it actually went above the final value. And you can also use the equation. I like to write the 100 in front so I don't accidentally multiply it in the exponential term. So it's 100 e to the negative and then pi zeta all over square root of 1 minus zeta squared. You can use that also in order to calculate the percentage overshoot. That one comes helpful when you only have the zeta value and you don't know the y final value. And then the next one is from this equation, you can actually derive how to calculate zeta from the percentage overshoot. So say you didn't know zeta, but you knew the percentage overshoot, you can use this equation, which will come in handy, which is negative the natural log of the percentage overshoot over 100 all over, and then this is the square root of pi squared plus the natural log squared, the percentage overshoot over 100. And so that one comes in handy in order to calculate your zeta value. And those would be the two really important formulas. You should definitely have these in order to calculate values. Say if you know the percentage overshoot, you can calculate zeta. So you know zeta, but you need to find percentage overshoot. So you can go to one or the other based on the information you're provided. And you can use an approximation technique. So within our class, there were 3 types of approximations you can do in order to calculate from the percentage overshoot. You can calculate zeta from this table. From zeta, you can calculate approximately how much percentage overshoot there must be. And then there is the graph of the percentage overshoot versus the damping ratio. So you can derive it either this way using the graphical technique. We like to use the table technique though more, so have the table definitely. There is this other graph here, which comes in help for if you have to calculate maybe the rise time or the natural frequency. Here, this would be important because if you know zeta, and you know either the natural frequency or the rise time, you can divide in order to solve for the other unknown variable from this graph. And so both those are helpful in order to approximate what you'll have to do in order to calculate one of those unknown variables to make a good estimation. So we're going to start out with an example because we had a lot of equations for second order systems. So given the transfer function, find the peak time, so time to peak value, the percentage overshoot, the settling time, and the rise time. And so our G of S is given as 100 all over, and then here we have S squared plus 15S plus 100. So the first thing that should be going into your mind, oh, omega n is equal to 10 because it's the square root of the constant in the denominator. And then your 2 zeta omega n s is equal to, and then here we have, oh, this is 15 times s. Sorry, I forgot the s up there. And so 15s, we know omega n, so I'm going to plug that in. So times 10 times s is equal to 15s. And we're going to have zeta times 20s is equal to 15s. Divide both sides by 20s, divide by 20s. You're going to get zeta is equal to 3 over 4. And so that is 0.75. Okay, so that makes sense so far. Now we have to calculate the peak time. Remember, peak time it is given by pi over omega d. And okay, so our peak time is equal to pi over omega d, which is equal to pi over, and then remember omega d is just zeta omega n. If you recall from when we were defining the second order system, omega d is equal to, and then, oh wait, let me see. Omega d is equal to, oh, sorry, wait, I was looking at the wrong one real quick. This one, when you substitute in for omega d, it'd be omega n square root of 1 minus zeta squared. My bad. And so this will be, if we plug in here, do we know our omega n? Yes. Do we know our zeta? Yes. So we can solve for this. And so it's going to be pi divided by, and then our omega n is 10. And then our zeta is 1 minus, and then our zeta value is 0.75. and then square that zeta value. Make sure you do the square. When you plug this into your calculator, you're going to get the result of 0.314. So we calculated the peak time here. And now we need to calculate our, let's see, can we do our overshoot? Yes, we can do percentage overshoot. Because remember, we just need the zeta value, which we have. So it's going to be 100 multiplied by e to negative pi zeta 0.75 divided by 1 minus 0.75 squared. And when you plug that into your calculator, you're going to get 2.8%. Okay, and now we need to find our settling time, T of S, which is going to be given by, and remember settling time, we defined it as 4 over sigma D. So that's what we have here. It's 4 over sigma D. Remember, sigma D, what is that? Sigma D is given specifically by looking at our formula sheets. It is zeta omega n. Remember, we can apply all these equations because the system is under damped. So because this is an under damped system based on our ratio, remember, that's why we can apply this equation here. So take that into account. Why we can be using these equations is because we have an under damped system because of our damping ratio. Just keep that in the back of your mind. So 4 divided by, and then zeta 0.75, and then times omega n, where omega n in this example is 10. And so when we plug this into your calculator, what you're going to get as a result, let me just clarify, make sure this is correct. 4 divided by, and then 0.75 times 10. I got 0.53. Okay, so now we calculated settling time. Here's our percentage overshoot. We need to calculate our rise time. So in order to calculate your rise time, what we're going to do is we didn't have an equation for this one, but we had a graph for this one in order to determine the rise time. And so looking at our graph, remember, this one gives you the rise time in omega n. So around 0.75 here, our rise time is going to be approximately 2.25. That's what we're going to have here. Remember, though, this isn't our rise time exactly. It's omega n times the rise time is around 2.25. So when we're solving this, we're going to say omega n times the rise time is equal to 2.25. This comes from the graph. Plugging in what we know for omega n, we know the rise time is given by 2.25 divided by and then 10, which is 0.225. And so those are all the values that we have specifically for our rise time. Okay, now that we have all these, let's move on to another example, because now we understand how we can actually calculate everything. And so let's do, let's see which one's better, which one requires more. Let's do the following one first, and we'll see how it goes, making sure we stay within our time. So for this example, for the following DC motor position control, find parameter K to achieve percentage overshoot equals, or sorry, is less than 5%. Okay, so they gave us here, we have our theta S goes into, then we have the summing block where we had the plus and we had the minus here. And here's our K, which is acts as our gain almost. And then we have our DC motor, which is 1 over, then it's going to be S times S plus 1. Notice that that is a second order system here because it has S squared, of course, but there's 2 poles. And then our output is going to be theta and then S. And this is going to go through to the beginning block. So for this DC motor control, we need to find the parameter K to achieve percentage overshoot is less than 5%. And so in order to do this, let's calculate what our transfer function is even here, because we know the input and we know the output, but we don't know what our transfer function is. And remember, when you calculate the transfer function, that's going to be everything right here within this feedback system. So T of S is going to equal, what's my gain up here in the open loop gain? This is going to be K times 1 over S times S plus 1 all over. And then remember, because it's a feedback system, 1 plus, and then what you have for your open loop gain, S times S plus 1 plus your feedback gain, which is just 1 here. So that's just multiplication by 1. Then we're going to multiply by the denominator of S times S plus 1. And so in our numerator, we'll just get K over, and then this would be S times S plus 1 plus K. And so then this is K. And then if you simplify, it would become S squared plus S plus K. Okay. Now we got it here. So recall your transfer function here is given. So we know what our system is. Isn't the omega n equal to the constant, the square root of it? So it's square root of K. And now that we know that, when we have to solve in order to determine our value, what we actually have for the zeta value, because that's what we need to focus on. What do we need for our zeta here? Well, remember when we're doing our calculations, in order to find our zeta, we look at what's the term right here. And so we have 2 zeta omega n s is equal to s. So we have 2 zeta omega n is equal to 1. And now that we're provided this, we need to, well, we know this overshoot has to be less than 5%. So looking at my table, what is the value zeta so that I have an overshoot less than 5%? Looks like right here, our zeta that provides an overshoot less than 5% is about 0.7 or greater. So zeta has to be 0.7 or greater is what we can tell from that chart. And so here, our zeta value, we know must be greater than 0.7. And what is zeta defined as when we had it here? When we simplified this one, you have zeta defined as, and then it's going to be 1 divided by 2 omega n. And so we can say 1 divided by 2 omega n must be greater than 0.7, just plugging in for zeta. And so here, what we're going to see is that omega n, when we solve for it specifically, so if we move omega n over to this side, then we would have 1 divided by 2 times 0.7. And we're going to get 0.7143 must be greater than omega n. So remember, our omega n was equal to the square root of K. So now just plug in for omega n square root of K. And then 0.7143 still over here. And now we're going to take the square root of both sides. So 0.7143 square root must be greater than K. And so when you take the square root of this, you're going to get 0.51 must be greater than K. And so what we did here is we were able to find K such that the percentage overshoot was less than 5%. Because we first found the transfer function of this block diagram system. From the transfer function, we determined our omega n, which is the square root of K, and we determined our value for zeta. When we were trying to solve for it, we found that zeta, in order to achieve a percentage overshoot less than 5%, zeta had to be greater than 0.7. Plugging in for what we solve for zeta is 1/2 omega n. And then solving for our omega n, we then plugged in what we got for omega n, which was the square root K, took square root of both sides. And that's how we arrived at our final answer, where we found what the value the gain must be in order to achieve a percentage overshoot less than 5%. And so that one is pretty important in order to have a good understanding behind the design aspect. And so now that we talked about that one, let's look at another example which has the design to it. So for this example, it's for the DC motor position control with tachometer. Find parameters K and KT such that, and we're going to have the percentage overshoot, this is the first condition, is less than 5%. And for the second condition, we have the settling time must be less than or equal 0.5 seconds. So the block diagram that they gave us here was, they had the theta R of T, and here it's plus going in, minus. They have the K for the gain, and then they have another summing block where it has minus T. And then here, the output is theta dot, so derivative. And then we have 1/s. And then our output's going to be theta s. And sorry, theta t. My bad. And then this is a feedback system here as well. Okay, so there's a lot here to look at specifically. So in order to calculate all of this, we need to find a transfer function of this entire system here from our input to output, because that will give us the second order system where we can find our values that we need in order to calculate our settling time from our zeta and our omega n. And so what we're going to do here is first look at this one. Let's calculate the transfer function of the interior first, and we'll work our way outwards. So the transfer function here, I'm going to call this T1 of S. T1 of S is equal to, it's going to be 1/s plus 1 all over 1 plus, and then this is KT 1/s plus 1. Which this is going to be equal to, multiply numerator and denominator by s plus 1. You'll get s plus 1 plus KT. And now we're going to have to find the entire transfer function of this whole thing here. So for this transfer function, I'm going to call it T of S, because that's the transfer function we're interested in. It's going to equal, what's going to be K multiplied by the one we have here, because it's just in series, in cascade, you can say, times 1 over, and then this is S plus 1 plus KT. And then it's in series with the 1/s as well, all over. And then it's a feedback system. So remember, it's going to be 1 plus K times 1 over s plus 1 plus kt. On the feedback loop, there is no specific block defined, so it's just a gain of 1, so it's multiplied by 1. And here, we're going to then multiply the numerator denominator by s plus 1 plus kt times s. So we're going to get k in the numerator all over. Then we're going to get s plus 1 plus kt, and then multiplied by s here plus, and then this would be k. And so when we simplify this, we're going to get k over, and we're going to get s squared plus, and then we're going to get kt plus 1 times s plus k. So that's just the simplification of our transfer function. And so from this, if we're going to calculate what we need, recall that here in our specific example, that this part determines our zeta when we're trying to find it. Recall from the problem we just solved, in order to get a percentage overshoot less than 5%, zeta had to be less than 0.7. So recall zeta had to be less than 0.7 here. Sorry, zeta had to be greater than 0.7. My bad. Okay, so zeta had to be greater than 0.7. And what we're going to see in this denominator specifically, remember we have 2 zeta omega n s is going to be equal to kt plus 1 multiplied by s. The s's will cancel. So you're going to be left with 2 zeta omega n is equal to kt plus 1. And then what we're going to do from here is that then we see, looking at what we need to do is we have our settling time. They told us how to be less than or equal to 0.5 seconds. And so since this is going to be our design aspect, we have our settling time. If you recall from the equation, is equal to 4 over, and then we have our zeta omega n, but this was equal to 0.5 because it could be equal to 0.5 seconds or less than. And so our settling time, what we can do from here is we know our zeta omega n is equal to 8. And so knowing that, what we can do is now we can plug in. So we looked at this condition here in order to determine here the value of our settling time. We set it as 0.5 because this is a design problem. So it's set at 0.5, so we got 8. And so now we can plug that in over here for 8. So we actually get 16 is equal to kt plus 1 because there was a 2 in front. And so kt was equal to 15 when you solve for it. And then knowing that, what we were able to determine from this is if you plug back in to, and then you have your zeta omega n equals 16, because we know that's the right-hand side of the equation now. Because recall that when you solve for kt, this is kt plus 1, so it's 15 plus 1, so that's why it's 16. You're going to see that when you have your zeta omega n equal to 8 when you divide by 2, recall your zeta had to be greater than 0.7. He did recall in the table, it was for 4.6, so it's fine if we set it equals 0.7. So omega n is equal to 8 divided by, and then we have our zeta, which is going to be omega n is 8 divided by, and then if we chose 0.7, that would still be fine because from the table is about 4.6 percentage overshoot. It shouldn't cause much of a difference. You can set it greater than a 0.7 if you want. You can set it at 0.8. Omega n is going to be 11.42. And from this, remember your omega n is equal to the square root of the constant, where omega n, we solved for it. We know what it is actually here. So since we know it's 11.42, plug it in. 11.42 is equal to the square root of k. Take square root of both sides. You're going to get k approximately equal to 130. So the first step we had here was we found the transfer function of the entire system. After finding the transfer function, we had our 2 zeta omega n s. We set it equal to this. We were able then to find from the settling time, we set it equal to 0.5 here. This is the design problem. So we solved for what omega n times zeta had to be equal to 8. Plug that in here. We got the kt, and then using that value we had, what we know the right-hand side of the equation must be, we solve for omega n, and then with that value for omega n, we can find out what the value of k must be, because omega n is equal to the square of that term, so we got 130, and that's how we got our result using that design problem. Okay, now that we got that, what we're going to notice a little bit is when we deal with higher order systems, we can do a little different of a calculations. Oh, I think this one might be important because it came up in the homework. So right before I talk about higher order systems, I think this one is worth mentioning for sure in order to ensure we don't make any mistakes on our exams. Okay, they gave us a problem where, for example, find the region on the left-hand plane where the poles of a second order system should be located such that the percentage overshoot is less than 10%. When you look at the table, you're going to notice that zeta then has to be greater than 0.6. And the second condition is the settling time must be less than or equal to 1 second. And so since we know the settling time, it has to be less than or greater than 1 second. We can set it equal to 1 second here. But remember, your settling time, it's going to be 4 divided by zeta omega n, which, remember, this is less than, so we can set that less than 1. And so we know zeta omega n must be greater than 4 when you solve for it. And recall specifically, when we talked about zeta can be calculated using what we know here. We know cosine of theta is equal to zeta. And when you do the calculation, you're able to see that theta is equal to cosine inverse of zeta. And your cosine inverse, remember we chose zeta to be, had to be greater than 0.6. So plugging in that minimum condition, we're going to see theta is equal to 53.1 degrees. Now looking at our plot here. In our plot specifically, we need to find the region on the left-hand plane, which is talking about this region over here, nothing on the right-hand plane. So what we're going to see when we do our plot is when we make the graph of these, it's going to give us, let me see if I have the good graph. For a graph, we're going to have for S plane, remember your theta is going to be the value here. So it's going to be around 53.1. This is theta, which is 53.1 degrees. And recall, when you have it up here, they come in pairs, complex conjugates. So that's why I drew it on both sides here. And then we know that so that was this first point right here. We know our zeta omega n must be greater than 4. Remember, along this axis here, this is negative zeta omega n, which then if we have negative 4 here, then it must be, so this would be at -4. It has to be everything to the left-hand side of this line. And then looking now, what is that area of overlap specifically? The area of overlap between those two conditions is given right here. So it falls within your theta value. Is remember, your zeta at most was, at the very minimum was 0.6. And so what we're going to see is we had 53.1. And so that is what determined what we had here. This was the very minimum condition we had for zeta. And so 53.1, if we were to make it any larger, it would just result in an angle that would be smaller. And so this would be the most that it could cover. It would never go wider than that angle. It would always be less than. And then here was our zeta omega n, because remember, this is negative zeta omega n when you're going in this direction. So if it's just negative, then it'd be negative on the other side as well. And so here, what we got was, when you take the negative, remember when you multiply by a negative, it changes the sign. So when you say negative zeta omega n, it's going to be, has to be less than -4, because you have to flip the sign when you multiply by negative or divide by negative. So that's why it's everything to the left-hand side of -4. Okay, so that's pretty much explains how you would graph that. Okay, now that we talked about that example, we're going to look at higher order systems. So high order systems. So this would be more than 2 poles. Because remember, if you have 1 pole, it's first order. If you have 2 poles, it's second order. So more than 2 poles. So for higher order systems, we can approximate them. So how can we approximate these higher order systems? When you have to approximate a first order system, it's going to look something like this. And here we go. So remember, this is your imaginary axis, j omega. Here's your sigma. And you have a pole, let's say here at -1. You have another pole at -5. And so if there exists a real pole and its distance to the j omega axis is at least 1/5 of the other poles, then the system may be approximated by the pole closest to the axis. So the big thing here is, notice that the distance, this is the dominant pole because its distance is at least 1/5 of the other poles. So since it is 1/5, 1 divided by 5 is 1/5, then you can approximate the system by this pole right here for your first order system. So here you approximate by pole closest to j omega axis if distance is 1/5 of the other poles. Okay. Now that we saw that, what we can do specifically is we're going to do an example here, which I think is important in order to understand. So can you approximate this system here where you're given g of s is equal to 1 over s squared plus 4s plus 1. And it's wanting to know, can you approximate this second order system with a first order? With a first order system. Okay, so we have to find the poles of the denominator. So you would do the quadratic. So you'd have s is equal to -b plus minus square root of b squared minus 4ac all over 2a. And so when you solve for this, you're going to get -2 plus minus, and then it's going to be rad 3. And so when you solve for -2 plus rad 3, you're going to get -0.268. When you solve for the second pole, -2 minus rad 3, you're going to get -3.732. What we're going to see here is this distance, is this one 1/5 of this distance? We'll do S1 divided by S2. Is that going to be greater than 5? And what we see here is when you plug into your calculator, -0.268 divided by -3.732, you get 32. Let's see, is that 0.268? 732. You're going to be able to tell that this distance, this pole is 5 times, because 5 times that pole is -1.34. So this pole is much closer to the j omega axis. So we have this pole compared to the other one. S1 is much closer than S2 when you do it. So its distance, it is greater. This one is more than 5 times greater than the distance here to the origin than this one. So what we're going to be able to say is when we make the approximate, when we write our approximate, it's going to be in our denominators s plus 0.268 to account the one pole we're approximating with. But in our numerator, you need to ensure it has the same gain. So what we're going to do is the DC gain of this, DC means the frequency 0, so this will be 0. So G of 0 is 1/1. So in order to assure the same DC gain, so notice from here, when you do the approximation, you need to make sure the DC gain, so DC gain, G of 0, when you plug in S equals 0, it's just going to give you 1. So here, ensure the DC gain matches. So you get the G approximate of 0 needs to equal 1. So that must mean our numerator needs to equal 0.268, because when S equals 0, it's going to be 0.268 in denominator, and you need 0.26 in numerator to give you a gain of 1. Okay, now that we got that, when you specifically do a second order system, when you're trying to approximate it, so approximating a second order system. In order to approximate a second order system, what you're going to notice specifically is if there are two complex conjugates, so that would be something like this, where you have 1, 2, and their distance to the j omega axis is at least 1/5 the distance of the other poles, then it can be approximated by your complex conjugates here. So it's the same thing where the d1 over d2, or sorry, the d2, oh, that's why. In this one over here, it's S1 over S2 over S1. That's why it was giving you an error. So here it's S2 over S1. The distance to this pole here, S2. And then this is the distance to these poles, S1 over S1 must be greater than 5. And so in order to approximate with these two poles here and disregard all the others, you have to look at the distance. And if the distance of the complex conjugates is going to be 1/5 of the distance of the other poles, then you can approximate it by the closest poles to the j omega axis. And make sure your DC gain is matched as well. And now when you have a system with zeros, so this is a system with zeros, zeros affect the amplitude of the response. but not the nature of the response. The closer the zeros are to the dominant poles, the greater its effect. And so the final one that we're going to see is pole zero cancellation. And for pole zero cancellation, what you're going to be able to tell is you never cancel poles and zeros in the right-hand plane. If a zero, now we're talking about the left-hand plane, if a zero is very close to a pole, it cancels the effect of the pole. Okay. So for the example, if we have G of S is equal to, and then let's say S plus, and then we have 1.05 all over, and then here we have S plus 1, S plus 10, S plus 100. You're going to notice that this 0 is very close to this pole, so they're going to cancel each other out. And your G approximate, what you're going to have is G approximate equal, it's going to be about you're going to have, make sure your DC gain is the same. So the DC gain here, that's a big thing, but we know in our denominator for sure, we're going to have, notice that at the same time, this pole, isn't the distance to this pole going to be much greater than the distance to this one? So if we approximate it with this pole, we're going to also notice that this one is going to have no effect. The majority of the response is going to be from this dominant pole. So we're just going to have S plus 10 in our denominator. And so what you have to take into account is here. What was the DC gain up here? G of 0 was 1.05 all over 1 times 10 times 100. And so that was 1.05 divided by 1 times 100. It was approximately, we have 0.00105. In order to ensure that same gain happens here, when we approximate it by S plus 10, we have to match this ratio. So when we have 0 here, we need to make sure that this one is kept alive. So if we have 0.0105, our DC gain of our approximate, G approximate 0, is going to equal, well, if you do that, divide by 10, you're going to get the same exact result here. So this would be the correct one, 0.00105, which matches. And so this would be our approximate equation. Okay, now that we learned that, that's basically everything you need to know about the systems, having a good understanding behind that and how the responses work. Now that we talked about the system response, we're going to get into the next part, which is going to deal with our steady state error. So I'm going to, okay, now we're going to talk about steady state error. So the steady state error is basically when we had our underdamped system here and it had the overshoot, then it damped for a little while, we noticed that the response didn't exactly match what the output, the value of 1, it was just like a little under it. And so this error here between what your response is and the actual output that you were hoping for is defined as the steady state error, that little marginal difference there. And so what we're going to see here is for a unity feedback system, which we're going to be going over. The unity feedback is R of S here, and that's our input, of course. Then we have it going through, and we have our error, which is E of S. Then we have the transfer function G of S. And then we have the output C of S. And this one goes through. We basically notice that the error, E of T, is defined as the input minus the output. And this input is known as our desired output, because that's what we want to see at the output, what we put in, where this one is going to be our actual output, what we're actually seeing at the output. So the difference between the two, which E of T is defined as RT minus C of T. And this is often written in terms of just taking the Laplace of these. E of S is equal to R of S minus C of S. And what you're going to notice from this one, of course, is your C of S. Can it be represented here if we have our R of S? C of S can be, it's the input multiplied by the transfer function. And so when we do the transfer function here for this, remember, transfer function of closed loop system with feedback is going to be G of S over 1 plus G of S times our R of S. And so we can say for this one that our error is just when you do the subtraction of the two, you're going to get the following. You're just going to get 1 over 1 plus G of S times R of S. And so the big thing to just notice from here is that the error is defined as the following in the time domain and then the equivalent in the frequency domain. But your steady state error is defined as the limit as t goes to infinity with E of t, which is the limit as s goes to 0 using our initial value theorem, s times E of s. And then here, since we solve for E of s, you can just plug it into here. So you would just plug in limit as s goes to 0, s times 1 over 1 plus G of s times R of s. However, the big equations you just need to know are these right here. And so different inputs you're going to notice here for your R of s are going to result in different steady state errors. Because of this term R of s, you're going to have a different output for your steady state error depending on what your input is. And so when we talk about system type, a lot of times, it's the number of pure integrators you have in your system. So a lot of time when they refer to it, an example, what is a pure integrator? Well, if we have specifically G of S given to us is equal to S plus 2 all over S squared plus S, you can rewrite the denominator as S times S plus 1 and then S plus 2 here. The pure integrator is the one that is by itself, the S term by itself. So your system type would be I is equal to 1. So the system type, just remember, is the number. So you define it with I. It's the number of pure integrators. And what's a pure integrator? 1 over S. Okay. So here we're going to have to find for our example with the step input. So this would be when we write this out, we're going to do for the unity feedback with the step input. So step input feedback system. Notice it's a unity feedback because it has the feedback, it has a gain of 1. There's no block in the feedback loop. And so here we have our R of S, and then we have our summing junction, and then we have our air. And then here it is G of S. Then we're going to get our output, which is C of S. And so for our steady state air, what you have to remember here is remember our steady state air is equal to the limit as t goes to infinity, and then E of t, which is equal to the limit as S goes to 0, S times E of S. And this is going to be, remember we calculated from right up here what our E of S was. We did R of S minus C of S, and we calculated what C of S. So I'm just going to use the result here for E of S. So it's going to be limit of S as S goes to 0. And then our E of S, plugging it in, what we're going to see is we get 1 over 1 plus G of S, R of S. And you will be able to tell that our R of S here, it's the unit step, right? So this is actually 1 over S. And so the S will cancel the 1 over S. And so you're going to be left with the limit as S goes to 0, 1 over 1 plus G of S. And so what you're going to notice is basically when we have this, we're going to be left with, we're going to call it 1 over 1 plus K of P, where K of P is going to equal the limit as S goes to 0, and then it's going to be G of S. And so that's what we're going to find, because here as S goes to 0, that's where a limit condition will be in. So it's just going to be 1 over 1 plus KP, and we define KP as where G of S is going to approach 0. And so that's what we're going to notice. If you want the steady state air basically to be 0, so remember, this is your steady state air. If you want it to be 0, you're going to make KP infinity. And so that's a big thing. You'll want KP in order to be infinity, so your steady state air is 0. And so now we're going to look at, so let me write down that note real quick, because I think it will come in handy. We want the steady state air equals 0. We're going to have okay. And that would be, okay. What you're going to see is if your G of S in here is going to be 1 over S, pretty much, it's going to make sure that the steady state air is going to be 0, because let me just write this note. If you have your limit, you have S going to 0, G of S. Remember, this is your KP. This is what we set it equal to. And so this would be limit as S goes to 0, and it's your numerator over your denominator, those two polynomials. And it's going to be limit, and then S goes to n0. If we put in a pure integrator, if we have a pure integrator in our denominator, so I'm going to make this d prime of S to just show it's different. We had a pure integrator in our denominator. This would, if you divide by 0, it's going to give you an air, and it's going to go to infinity. So if we make this term go to infinity, then the air steady state is basically 0. So in order to ensure that the steady state air, so to make sure that the steady state air equals 0, we make sure system type is greater than or equal to 1. Because if our G of S has a pure integrator in it, then it's going to for sure go to infinity. So this KP goes to infinity. And so 1 over infinity is going to be 0. So that's how you get the steady state air 0. Now, what if we have a ramp input for unity feedback system? Unity feedback system. Okay, and remember it's given by RVS, and then we have a summing junction where this is plus, this is minus, and then we have our error, this is E of S, and you have this as your G of S block, your transfer function block, then you have your output, which is C of S, and then here is your feedback. And so what we're going to notice, remember your steady state error, always start with this. It's going to be limit S goes to 0, E of S, E of S. And we know what our E of S is, recall from the previous example, it's going to be 1 over 1 plus G of S times R of S. And this is a unit ramp. And remember for your unit ramp, your R of S is going to be, because it's a ramp input, R of S is going to be 1 over S squared. So the S will cancel with one of the S's. So you're just left with, it's going to be the limit as S goes to 0, 1 over S, and then multiplied by 1 over 1 plus G of S. And so here, if you multiply that S into the other term, you're going to get the limit as S goes to 0, and it's going to be 1 over S plus S G of S, which is going to equal the limit as X approaches 0, 1 over, and then here, what we're going to see is when we separate these two from one another, we're just going to get S G of S. You're going to notice that we ignore the term right here because we just we plugged in the 0, so it just disappeared, but we still kept in this one, which he defines as the 1 over KV, and KV is defined similarly to the other, but it's the limit of SG of S as S goes to 0. And so this KV is known as the velocity error constant. KP was known as the position error constant. And so what we're going to be able to tell from here is if we have our steady state error, basically, when I equals 0, there is no S in the denominator to cancel, we're going to see that our position constant is going to equal. So if our I equals 0, our system type equals 0. So G of S is just a number. There's no 1 over S. So that would just be G of S is a finite number. So just a finite number. Then here, so our KV would just be 0, right? So KV equals 0. And then 1 divided by 0, your steady state error is going to equal infinity. Well, if your I equals 1, then you're going to have a pure integrator, so it will cancel for your system type. So then your KV, so G of S would equal 1 over S. And so your KV will equal, well, that will cancel. So it's just going to be 1. And so your error steady state is going to equal, and then it's a constant because it's going to be 1 over 1. That's just a constant number 1. I equals 2. Then you're going to have G of S is equal to 1 over S squared. So your KV is going to equal, here we're going to have, if we have over S squared, we're going to have 1 over S left. And so then we're going to have the S in the numerator. And so with the S in the numerator, basically, we're going to see, because we have 1 over S squared, it would be 1 over S. So this would go to infinity, but 1 divided by infinity, this would be 0. So this one goes to infinity. So your error steady state equals 0 then. Okay, now that we define that, the last one is the parabola input. In the unit parabola, the big thing you need to know about that one is it's just 1 over S cubed instead of 1 over S squared. But we have a table based on your position, your system type. So the system type, this is the important table, make sure to have down. System type. So you can have either 0, 1, 2, or 3. And then you can have your input, which your input can either be the step input, so that's 1 over s. It can be the ramp input, so 1 over s squared, or it can be the parabola input, 1 over s cubed. And so we saw for system type 0 for the step input, it's going to be your 1 over 1 plus kp. For your ramp input, it was infinity, and for your parabola input, it was infinity. Then for system type 1, this was 0, and for anyone greater than their steady state was 0. But for your unit ramp input, for system type 1, you finally got constant, and then you got 0 for the others for your air steady state. And then for this one, the unit parabola, you won't get it until system type 2, you'll get a constant, and then after you'll get 0. So this defines your air's steady state based on the type of input you have. If you have a step, if you have a ramp or parabola, and your system type for your G of S. If your G of S has no pure integrators, if it has 1 pure integrator, 2 or 3 pure integrators. And so let's do an example in order to understand this. So given the following unity feedback system, so given the unity feedback system, in here what we have within our unity feedback system is we have our R of S goes towards, and then the summing block, where here our G of S, so this is the E of S, of course, because it's a C of S minus R of S. Sorry, it's R of S minus C of S. Our block here is going to be 2 over S plus 1 times S plus 2, and then it goes to our output C of S. Okay, so here, what is your system type? There's no pure integrators, right? Because it'd have to be a 1 over S. There's no just S by itself. So the system type I equals 0. The steady state air, if the input, so what is the air steady state if input is 5u of t? Well, that's going to be 5 over s, remember? So your steady state is going to be, in order to calculate that, you would have your air steady state is defined as, and then it's going to be 5 over, because that's the amplitude of your input, 1 plus kp. And remember, your kp is defined as the limit as s goes to 0, g of s. And here we're going to see it's going to be the limit as s goes to 0. And then if we plug in our S0 here, you're going to get 2 over, and then it's going to be 1 times 2. And so you're going to get 1. And so it's going to be 5 over 1 plus 1, which is going to be 5 over 2. So that's going to be your steady state air. It's going to equal 5 over 2. If that is your input 5ut, because 5ut, if you look at the table, if you have the input, remember that's just 5 over s in the Laplace transform. So 5 over s. So 5 over 1 plus kp. This is your steady state air in between here. So all these values here are your air steady state. This is based on your input right here, of course, this row. And so that's what we did. We calculated, remember the position error constant is given by kp, where it's defined, we had it as a limit, s goes to 0, g of s. What is the steady state error if the input is given by 5t u of t? And so this is the ramp. So we're going to have a over s squared. Our amplitude is 5, so it's going to be 5 over s squared as our input. So 5 over kv is going to be our air steady state. So our steady state air is going to equal 5 over kV, where our kV is defined as the limit of S G of S and as S goes to 0. And so multiplying by S, our G of S here, we're going to see that we're going to get 2S all over, oh wait, our G of S here is going to be 2 times S. It's going to be 0, yeah, because it would be an S in the numerator. So it's going to be 0 all over, and then what we have. And so that will just be 0 over 2, so it's 0. And so what we'll get here is we're going to get 5 divided by 0, and so that's going to go to infinity. And so this will equal infinity. And remember that these are defined, of course, for our unity feedback systems up here. So this is a really important table to use in order to define your examples and have a good understanding behind it in order to know what your air steady state is. Now we're going to go to the next example where we're going to look at the following unity feedback system. So let's examine this one. So we have our R of S, so we have our input, and it goes towards the summing junction. And for our air, of course, because it is given by R of S minus C of S, then goes through a system. And the system is defined as 100 times S plus 2 times S plus 6 all over. And then it's going to be S times S plus 3 times S plus 4. And then here it's going to go, and then our output is C of S. And so what is the system type? We have one pure integrator, so our system type is going to be I equal to 1. And then looking at what is the steady state air, so air steady state if input is 5 U of T. Well, our steady state air, we have to look at this. Okay, so we have the unit step, so it's going to be 5 over S, and it looks like we have one pure integrator, so it's 0. And then air steady state if input is 5T U of T. Okay, if it's 5T UT, we have the unit ramp as the input, and so this would be 5 over S squared. And we have one pure integrator, so it's going to be A over KV. So the air steady state will equal 5 over KV. Remember, your KV is defined as the limit of S G of S as S approaches 0. And so this is going to be, we're going to get 100 and then S plus 2 times S plus 6 all over S plus 3 times S plus 4, because those the S and the S in the denominator here will cancel. And so this will be the limit as S goes to 0. And we're going to see we get 100 times 2 times 6 all over 3 times, and then here we have 4. And when we solve for that, you're going to get 100. Because this will just be 12 divided by 12, so it's just going to be 100. And so here we get 5 divided by 100. You're going to get, when you do 5 divided by 100 in your calculator, 0.05. Okay, so we're able to determine the air steady state from this unity feedback system. Now, we're going to be given a design question. So this example will give us the input R of S, and they're going to have the summing junction here. And then we have our air E of S, and this will have K times S plus 5 And then in denominator, we have s times s plus 6 times s plus 7 times s plus 8. And it's going to have an output, which is given by c of s. And here, we need to determine the parameter of k. So determine k such that the steady state error, so the steady state error to r of t, which is of course the unit ramp, is less than 10%. Okay, so here we need to make sure steady state error, and we have the unit ramp, right? So we know that our steady state error, basically when we have the unit ramp as our input, we know it's a over s squared. And we want to make sure that our steady state error is less than 10%. Well, right here, we have infinity for steady state error, but here we get a constant. So we need to make sure that that steady state error is less than 10% here. So what we're going to try to achieve is for error steady state, the 1 over kV, where we actually get a constant number, we want to make sure that it's less than 10 over 100 because that's 0.1, which is 10%. So we need to ensure that kV is actually going to be greater than, and then when you multiply kV in order to get it into the numerator, it's going to be greater than 10. And so remember, our kV is defined as the limit as s goes to 0, sg of s, which is the limit as s goes to 0, and then having our s in this, so it would be s times k, s plus 5, all over, and then we're going to have in the denominator here, s times s plus 6 times s plus 7 times s plus 8. What we're going to see happen is that these s's will cancel, and we're going to be left with, when we plug in R0, it's going to be k times 5 all over, and then we're going to get 6 times 7 times 8. And here, when we solve for that, remember, our kV has to be greater than 10. That's what we set up here. So when we simplify this, we get 5k over, and then 6 times 7 times 8, you're going to get 336. And this has to be greater than 10, because that's what we define here. kV had to be greater than 10. And so when you solve for k must be greater than 672. And so when you multiply by 336 over 5, you get the value of k. And that's what we'll get here in order to calculate it. Okay, now that we talked about that, we're going to do the following, where for the next example, we're going to consider okay, yeah, that one he said you can skip, so I don't think he'll examine that one. Consider following input discernment. Okay, this one's an important one because it introduces the topic of disturbance, and disturbance is a little different. So we have to calculate the steady state error with disturbance. So what is disturbance? Well, if we have a unity feedback system, so unity feedback system with input R of t and disturbance d of t. We're going to calculate the steady state error. And so here, how that looks like when we have a disturbance is we have our input still, and it goes through a summing junction block. Sorry, this would be our minus, and then our error, which is E of S. And then it's going to have the controller, which is the first one, which is our G1 of S. So this is known as the controller. And then we have the disturbance here. And so this is our D of S. And then it goes through the plant. And our plant's going to be G2 of S. And then we're going to get our output, which is C of S. And it goes back. We have a feedback system. So remember, in order to calculate the steady state error, E of S, remember your error is defined as R of S minus C of S. And so we need to calculate what is C of S here. We know what our input is, but we don't know what our C of S is. And so we have to look, what is our output when we have no disturbance, and what is our output when we have no input? And then we sum the two together using superposition to find out what C of S is. So C of S is equal to G1 over G times G2 all over 1 plus G1 G2 R of S. When, and then this would be due to your disturbance being 0. In your C of S, you're going to notice it's going to equal G2 all over, and then it's 1 plus G1 G2 times D of S when your input is equal to 0. Because this will come before, so it will treat this one like the feedback. So that's why it's in the, we're going to see, it will, when you consider your D of S, it's going to treat G1 of S as your feedback. And the other one, you notice when we just had the ramp, these two were both in your open loop gain. They weren't in the feedback. So that's why here we have no G1 in the numerator, because D of S came after the G1 of S. So it treats this as in the feedback path. And so that's why it's only in the denominator here. And so our C of S, remember, it's the superposition of the two. So it's going to be G1, G2 all over 1 plus G1, G2 R of S. And then plus G2 all over 1 plus G1, G2 D of S. Okay, so we got it this far. Now we need to determine our error, which was R of S minus C of S. And now we found the total C of S. And so here we'll define our error as R of S minus G1, G2 all over 1 plus G1, G2 R of S. And then minus, of course, the other part, which is G2, 1 plus G1, G2 D of S. Now that we have that, what we have to do is we're going to notice R of S, if you subtract it from this one, you're going to get 1 over 1 plus G1, G2 R of S. And then here we're going to have minus our G2 over 1 plus G1, G2 D of S, which this is going to equal your total error, E of S. Okay, so this is the error due to, right here, E R of S, we're going to call it, the error due to your input. And this is going to be the error due to your disturbance. So this would be your E D of S. Let me make sure. And so what we're going to say is that if you make G1 really large, it's going to make the error minimal. And so if G1's really large, the denominators of both become really big so that it has no effect here. So the total error is given by the summation of the error due to your input and the error due to the disturbance. Now that we talked about that, let's look at finding for the following system. Let's look at the example. Find the steady state error due to the unit step disturbance. Okay, so we need to find the error due to the unit step disturbance. And so they give us specifically the block diagram, which is R of S. And then it goes through summing junction. And here, the E of S, the error, it's 1000, which is your controller G1 of S. And then here, it's going to be your disturbance, which is going to be your D of S. And then you're going to have your next one, G2 of S, which this one is going to be given as 1 over S times S plus 25. And then here is your output, which is C of S. Okay, now that we have this here, what we're going to notice is that we need to find the error due to the unit step disturbance. Remember, the error due to the disturbance is given by this equation here. This is our G1, this is our G2. Let's just plug it into our equation. So our error due to the step disturbance is going to be given by, so our error due to the step disturbance is negative, and then what's our G2? 1 over, and then S times S plus 25. And then all over 1 plus, and then G1 is 1000. And then times 1 over S times S plus 25. That's our G2. And then this is all multiplied by the D of S, which we know for this one, it's the unit step. And so then we'll replace our D of S, of course. This one's going to be our 1 over S. And so we can substitute in for this. We know this is 1 over S. It's the unit step disturbance. So when we have to find the steady state error, remember, this is the error, but this is not steady state error. Remember, error steady state is the limit as S goes to 0 of S E of S. So what we're going to notice is this S will cancel with the 1 over S, so we're just left with this term. And so what we're going to get specifically, you will see, is when we simplify this, it's going to be -1 all over, and then here we have our S times S plus 25, and then it's going to be plus 1000. And then we're gonna remember it's the limit as S goes to 0. If we plug in S equals 0, we're gonna get -1 over 1000, which is going to be -1 divided by 1000. So notice that this error is small. 1 over 1000, that is going to be -0.001. And so this error is pretty small, which for a steady state error, that's good. We have a small error, but it's small because our G1 is large. Remember, when you make G1 large, the error diminishes. And so that's why we have a small steady state error. Okay, now that we saw that pretty much, we're going to talk about how can you turn a system into a unity feedback system if it's not provided, so that you can use all these nice representations we have, all those equations that we just found. We'll say if we were given a system per se, and it had an R of S, and here's our summing junction. And this is our G of S, and then here we have an H of S. And so through this, we're going to have our C of S, which is our output. And so what we need to do is we need to transform, this is non-unity feedback because we have a gain in the feedback loop. And so we need to transform the non-unity feedback system into a unity feedback system. So what we're going to do in here is we're actually going to, you'll see, put in a -1 gain and a +1 gain, because right, those should cancel each other out. They're in parallel, so they'll just add together. So that's what we're going to do here. We have a -1, we have a +1 for the opposite one. These in parallel, these would just cancel each other out, correct? And so here, what we're going to notice is that then this block diagram, if we simplify these two right here, so we get, let me redraw it. I think it will look better if I show you guys. If we have our G of S, and then per se, this down here is going to be your H of S -1. And then we're going to have it going back into here. We have our R of S, of course, as our input. We have C of S. And so this one is going to be +1 still. We still have the +1 here, but now we're going to simplify these two. So we have the +1 on the unity feedback only. And so simplifying those two, you would do G of S and then all over 1 plus G of S and then times H of S -1. And so you should get the following representation here, which is going to be your R of S. Then you're going to get your G over 1 plus G times H -1. Okay, and then this will be your output C of S here. And then you're going to have that unity feedback 1. Okay, and so that is how you would develop a unity feedback system from something not with unity feedback. You do -1 and +1. Remember, in parallel, they add together. So this is really just a 0. It's not really doing anything. But then you would combine H of S with the -1. And then you combine the G of S, which H of S -1. And so you just get the unity feedback on the exterior one. And so with that, then you're able to determine your error, because with your error, you would just calculate it as C of S minus R of S, and then recall that your C of S is going to be R of S times this. And so that is how you could find your unity. You could transform a non-unity feedback system into a unity one, which is important in order to apply all the equations in the table we found. Okay, now we're going to be talking about the subject of sensitivity. Sensitivity is an important topic as it is the degree to which changes in system parameters affect system transfer function or performance. And so the sensitivity is defined. What we see it, I like to always put it as sensitivity of A, and then here's our transfer function T. So it's the partial of T all over the partial of A multiplied by A over T. And so that's what I like to call the sensitivity. I find that easier than what he gave us. So remember, this is partial. So that's the equation for sensitivity, the partial of the transfer function over the partial of A times A over the transfer function. And so let's look at an example where we're going to find the sensitivity. So example, find the sensitivity of the closed loop transfer function to changes in parameter A. Okay, if we have changes in parameter A, look here, we have our input R of S, and it's going to go through a summing junction, which this would be the positive, this is the negative coming in, and then this would be E of S, the air. And so this would be your K. So this is your over S times S plus A. Then this is your output C of S. Then you have it going back in your feedback loop. So we need to calculate the transfer function. That's what the sensitivity requires, the T here. So we need to calculate the transfer function of this closed loop system. The transfer function is going to be equal to your output over your input. And so that's going to be, your output is going to be given by, remember your transfer function here. If we have this, it's going to be the open loop gain. So it's G of S all over 1 plus G of S times H of S, where H of S is 1. So that's why we're going to get K over S times S plus A all over 1 plus K over S times S plus A, which this is going to be equal to K over S squared plus AS plus K. And then if we need to find the sensitivity, remember sensitivity of T with respect to A, lowercase a, because that's the parameter that we're looking at and seeing how it's sensitive to the transfer function. What we're going to see is we need to take the partial of T all over the partial of A multiplied by A over the transfer function. So that's going to equal, well, we have to take the partial derivative of our transfer function. And notice that this is going to be a little bit tricky, not bad, but we have to take partial and then we have to multiply by A over the transfer function. So when you're working with a fraction, you have to take the derivative of this. Remember that when you have a fraction, it's equal to the derivative of the denominator, sorry, the derivative of the numerator. So this is V, U divided by V. So it's derivative numerator times the denominator minus the numerator times derivative denominator all over, and then this is going to be your denominator squared. So what's going to happen is when we take the derivative of our denominator here, we're going to see that the derivative of the numerator is a constant, correct? So this would just be 0, and 0 multiplied by V is just 0 minus, and then we're going to have our numerator times the derivative of the denominator. So it's going to be K from the numerator multiplied by, and then we're going to have, if we take the derivative of our denominator, what we're going to see is it's going to give us, he did minus SK. Why didn't we have minus SK? Okay, because this would be K, and then he had just, oh yeah, because it's just derivative the one we're taking, because we're taking the partial with respect to A. So the only one denominator with A in it is the AS. So if you take the derivative of this with respect to A, you're just going to get S. So that's why we got minus K times S, because the K came from the numerator. And then taking the partial derivative of the denominator with respect to A, you'll just get S. And then all over that denominator squared. And so with this, what you're going to have is plugging in specifically for this part here, we're going to have our negative S of K all over. And then here we're going to have our S squared, and then plus AS plus K squared, and then times A over T. This one's going to be multiplied by A, and then our transfer function here we determined was K over S squared plus AS plus K. Okay, and then when you solve for this, your answer is going to be, when you simplify the result, negative AS over S squared plus AS plus K. That will be the result. And so that's what you will get. And so that is the sensitivity of the transfer function with respect to little a. And so that's a good example in order to practice. And so now that we looked at that, we're going to get into our final chapter. Okay, now we're going to talk about stability and its importance. And so in order to understand stability, what does stable mean? It's basically, when we talk about stability, we want it to decay in time. We don't want it growing in time. So what do I mean by that? For a stable system, we're going to see that as time continues, that it's going to slowly die out. It's going to go down, down, down. So we're going to notice if you make the envelope of this, you're going to see that it goes downwards towards 0. And so that is going to be the topic that we're going to look at now. And so whenever you have your output, basically, when you have a system, when you have the input and then it goes through a system to produce the output y of t, stability, basically what we're looking at is when we see the total response of the system, the total response, which is given by y of t, is going to be composed of 2 parts. It's going to be composed, the first part will be the forced response. And this is due to external input. And then you're going to have your natural response. And this would be due to like the initial conditions. So those are the 2 types of responses you're going to get that create the total response. So oftentimes we define the total response as yt is equal to the forced response plus, and then the natural response, the initial conditions component. So now that we see this in the frequency domain, you often represent it as the force one is due to the transfer function multiplied by the input. And then the natural response, that's due to your initial conditions. Basically, you'll have some polynomial that's due to your initial conditions all over, and then your denominator d of s. So that's just a way of knowing what we're talking about. And so when we talk about internal stability versus external stability, well, due to the internal or the initial conditions, that's where your y natural comes in. So internal stability, when we talk about that, it refers to the natural response of the system. So y natural t. And so that is very important versus external stability, which is the forced response. So that's due to the input you're putting into the system. So this is going to affect the y forced of t. And now that we need to see this, a lot of times we need the right amount of external force to stabilize the system. Because some systems aren't stable. And so you have to apply a force in order to stabilize them. So that's why we use external stability. So think of a pendulum. When it's inverted, it's going back in, when normally it goes like back and forth, back and forth. But if you flip it, it's going to naturally want to fall back down. So it won't go back and forth. So you have to apply a force so it keeps going back and forth if you're to invert the pendulum. And so what we're going to notice is that when we talk about internal stability versus external stability, this will be a huge differentiating factor that you have to make sure you're aware of each. And if he's asking if it's internally stable, you know that what it means. So it's internally stable if, so here it's stable if y natural of t goes to 0 as t goes to infinity. So it dies out. That's basically what it's saying. And it's going to be unstable if y of t grows without bound. So that's basically, it goes to infinity as t goes to infinity. And it's marginally stable. So it is marginally stable when y of t neither decays nor grows as t goes to infinity. So this could be like a cosine waveform, or it could just be a constant. That's what marginally stability could be. So what we use for this when we talk about internal stability is oftentimes we have the absolute value of x of t must be less than or equal to some number that is less than infinity. So that means it is bounded. So here, when we have our, let's say, signal, and we want to make sure that it is, if we take the absolute value of it, that it is less than some number, and that number is not infinity. So here, if we have m, it is less than m when we flip this, because this flipped would just be right here. And so it is less than m, and so that is less than infinity, so it is bounded. It's not going to pass m, and it's not going to approach infinity. So m is just some finite number. So it is less than this finite number, and so it will never approach infinity. So it's just saying that this is a bounded signal. And now when we talk about external stability, it's also known as the bounded input, bounded output stability. For every bounded input, you're going to get a bounded output. That's what it means. So what you need to do is your x of t is basically going to be less than n. And so there's going to exist a constant such that for x of t is less than that constant for every value of time. And so it's unstable if a bounded input yields an unbounded output. So for this one, it is stable if every, and then I'm just going to use bounded input results in a bounded output, and unstable if a bounded input results in an unbounded output. Okay. And now that we talked about that, basically what we're going to say is when we talk about an LTI system and we have to find the stability of this linear time invariant system, we have to look at where are the poles located. And so now that we talked about the internal and the external stability, a big thing for when we talk about the locations of the poles, because that helps us know whether or not it is bounded input or bounded output. So another definition for these is basically when we are looking at the graph. So this would be a graphical analysis of stability. When we deal with the bounded input, bounded output condition, it's stable if all poles of the closed loop system are in the left-hand plane. But it's unstable if one pole is in the right-hand plane. If you have two or more, so one plus poles, so it can be one or more poles in the right-hand plane. And then it's marginally stable if all the poles are in the left-hand plane or on the j omega axis. And so that's the big thing we basically have to determine. So a lot of times we look at the graphical technique. And so here, you're going to notice that these in the right-hand plane are unstable. They're going to infinity. They're going to infinity, going infinity, going. This one's growing, going to infinity. But the ones that are on the j omega axis, they're marginally stable. They're not growing, but they're not decaying. And the ones on the left-hand plane are decaying as time goes to infinity, what we see here. And so that is just a good example of how we have to determine the stability of our systems based on the graphical analysis. And so let's look at a few examples in order to build a better intuition behind the topic of stability. So for the first example, it says determine the stability of the system. So for this example, determine the stability. And so we have our R of S, and then it goes through, and here's our system 10, S plus 2 all over. And we have S plus 1, S plus 3, S plus 4. And then it's going to be C of S as our output. And so for our system, notice where are our poles, where are our zeros going to be. And so what we examine is, remember, for stability, it was just worrying about the poles. It wasn't worrying about the zeros. So notice that this is only dealing with poles. So for stability, just look at the poles. Don't care about the zeros. Okay, here we go. Here is one's at -1, one's at -3, one's at -4. So one's at -1, one's at -3, one's at -4. And so ours is stable because all the poles are in the left-hand plane. So this is stable. Yay. Okay. Now that we determined that, basically, what if we had one pole on the axis? Then it would be marginally stable. If we have a pole, say if it was like right here, then that would result in the condition of marginally stable. Just so you guys know, you're aware of that. Okay. Now that we talked about that, let's get to the next example where we're going to use the criteria. Let's look at this one. Determine the stability of the following system, where we're going to get this one here, I think is a good one to practice. Okay. So for this example, it's going to be determine the stability. Where we have our input R of S, and then it's going to go through, and then here is our summing junction, negative. Then our G of S is given by 3 over S minus 1, S plus 2. And then we get our C of S. Okay. So for this one, what we have to do is we have to find the transfer function first of the system. So we have to get the system function. It's going to be G over 1 plus G. And so when you solve for this, you're going to have 3 over S minus 1 times S plus 2 all over. And then you're going to get 1 plus 3 over S minus 1 times S plus 2. And here we're going to notice that when you solve this one, when you simplify, you're going to get 3 times S minus 1 times S plus 2 plus 3. And this is going to result in 3 over S squared plus S minus 2 plus 3. That'll be minus 1. Oh, wait. No, it'd be plus 1, sorry. Minus 2 plus 3. Okay, now that we got that, we have to find basically our poles for the denominator and just use the quadratic formula. So negative b plus minus square root b squared minus 4ac all over 2a, which is going to be negative 1 plus minus square root of 1 minus 4 negative 3 all over 2. Okay, now we're going to get, when we have this, it'd be negative 1/2 plus minus, and then it'd be j rad 3 all over 2. And when we plug this in, we're going to get 3 all over, and then we're going to get s, and then it'd be plus 1/2 plus j rad 3 over 2, and then s, and then it'd be plus 1/2 minus j rad 3 over 2. Okay, so that's what we would have here. And now that we have that, we'd have to plot our poles. And so notice that our poles are going to, that'd be at negative 1/2 plus minus j rad 3 over 2. So negative 1/2, then we're going to get j rad 3 over 2. Let's say that's about there, j rad 3 over 2 minus j rad 3 over 2. Okay, now that we got that, and this is stable because the poles are on the left-hand plane. And so we're good. So this is stable. Remember that in order to do this, you had to make this, you had to turn it into our, you had to find the transfer function because you were just given it, you're given with unity feedback, but you need to find the transfer function like we had in the previous examples first. You can't just plot this because this would be like, oh, this one's on the left right hand plane, so it's unstable. You have to find a transfer function first, and when you close the loop, it makes this stable. So that's why whenever you have a closed loop feedback system, when you close the loop, it makes it a stable system. Okay, now we're going to be using the Roth-Hertz test. The Roth-Hertz test is commonly used within control systems because it tells you about stability criteria. Okay, I guess here, let me write it out for you guys because it tells you important things. It doesn't tell you the location of the poles, but it tells you the nature of the poles. So it tells you how many closed loop poles are in the left-hand plane, the right-hand plane, and on the j omega axis. But does not tell you not the location of the poles. And so what you're going to be dealing with a lot is we're going to see that you're going to be dealing with the characteristic polynomial of the system G of S. And so we oftentimes look at our denominator. So I think it's best to know the Roth-Hertz to learn it through an example. And I think that is our best technique for this one. So let's do the example here. Determine the stability of the transfer function. And so they gave us the transfer function where they said g of s is equal to, then it's 10 all over s cubed plus 10s squared plus 31s plus 1030. Okay, and in the Roth-Hertz criteria, you use the denominator polynomial. So you're going to make your denominator polynomial, which is d of s. It's going to be s cubed plus 10s squared plus 31s plus 1030. Okay, we're expecting 3 roots because it's to the power of 3. So we're going to have our table s cubed, s squared, s to the power 1, s0. And what we have within this table is for the s cubed, the coefficient's 1. Then you look at the next one, which the odd one. So it's 31 is the next coefficient. Then for the even coefficients, 10s s squared, and then you have 1030. Okay. And then what you're going to do is you can simplify. So notice here, we can simplify this row. We can divide by 10. And so this would become 1 and 103. And then we're going to do, for the Roth-Hertz table, you find the determinant, the negative of the determinant. So you go in this direction and you go backwards. So it would be, for this position right here, it's going to be 1 times 103, and then minus, and then it's going to be 31 times 1 all over, and then it's all over what's in the bottom left corner, which is 1. And then you apply a negative on this one. So you do make sure you have a negative in there. And so it's going to give you 1 times 103 minus 31. Plug that into your calculator. 103 minus 31 divided by -1. You're going to get a -72 for your result here. So you get a -72. And then for the next one, for this position right here, you would go from this one and you would take what's in this position, multiply it, and then you go backwards, take this one and multiply it by the one right here. And you're going to notice, though, you're going to get 1 times 0 minus, and then it's going to be 0 times 1 all over -1, which is going to be 0. So that's why there's a 0 here. And then for this position down here, which is going to be your one right here, you're going to go from the one up here, you're going to go through. And so the determinant is going to be 1 times 0 minus, and then 103 times -72 all over, and then negative and -72 is just 72. And so you're going to get 103. And so with this, we're going to notice within our table that there's a sign change. It's 1, 1, -72, 103. We're going to look at the first column only, and you'll notice there's a sign change from 1 to -72 to 103. And so there's another sign change. There's 2 total sign changes. One from 1 to -72 and one from -72, 103. So because we have 2 sign changes in the first column, and results in 2 poles in the right-hand plane. And then that must mean we're expecting 3 total poles, right? And so there must be 1 pole in the left-hand plane. And so that's where the location of our poles are, and that's what the Roth-Hertz criteria tells us. So since there are 2 poles in the right-hand plane, this is unstable. Okay, now that we talked about that, we looked at specifically the number of poles. Okay, we're gonna find the range of K. So this one's gonna be a little different. That's gonna cause a closed loop to be stable. And so we're gonna do this example where it says find the range of K, or of gain K, that will cause the closed loop system to be stable. And so they gave us R of S, and then it goes through the summing junction where we have here E of S, then K all over S times S plus 7 times S plus 11. Okay. Then we have C of S here as our output. So within here, if we have to find, we need to find the transfer function first. And that will determine our raw hertz, what we're going to plug in for a denominator. So here, in order to find a transfer function, or T of S, we need to calculate. It's going to equal K over, and then here, just moving because I know it's going to move over here, S times S plus 7 times S plus 11 plus K. Okay. And then when we simplify this, we're going to get K over, and then here we're going to have S cubed plus 18S squared plus 77 S plus K. And when you work it all out, and then what we're going to do is we'll make our raw hertz table. So raw hertz table, it's going to start, our highest power is S cubed, then we're going to go S squared, S1, S0. And what we're going to notice is for the S cubed, which we're looking at our denominator here, remember you look at the denominator for your raw hertz, the coefficient's 1, coefficient in front of the S is 77. And then looking at the denominator polynomial, we have the coefficient of 18 here, and we have the coefficient for S to the power 0 is K. And now we're going to do our determinant in order to get it. So we're going to get, what we'll see is it's going to be K minus 77 times 18 all over negative 18. And then we're going to get here, if we do it 0. And then what's going to happen for next one is it's going to be K right here. And so remember, we need to make this stable. We need to find the range of gain that will ensure that this closed loop is stable. So in order to be stable, all the poles must be on the left-hand plane. So there must be no sign changes here. So in order to ensure there's no sign changes, we need to make sure that this value K minus 77 times 18 all over negative 18 is greater than 0, and K is greater than 0. So here we're going to have, if we look at this in particular, we're going to need multiplying this side by 18 and then moving this over to the other side. What we're going to get is K minus 77 times 18 must be greater than 0. And then add that over to the other side, so that we're going to get K times 77. K must be, and then it's going to be here, this would be, oh, because remember we multiplied by negative, that flips the sign. So that's why it would flip here. And then we're going to get K is less than, and then negative 77 times 18. You'll get that on this side, 77 times 18. And then here we still have K must be greater than 0. Yeah. So then this one will be the other condition needs followed, but K is less than, here's my calculator, 77 times 18 is 1386. And so your value for K must between 0 to 1386 in order to ensure that the system remains stable. And so that's what we have here. And now that we talked about that, let's look at one where we have special cases. And I think these are really important in order to understand and do well. So the special cases of the Roth-Hertz criteria is you either have zeros in the first column or the entire row is 0. So here, what we're going to notice is that so let's look at case 1, which is 0 only in first column. So what does that mean? Say if you have your Roth-Hertz, the highest power is n. So then S of n minus 1, of course, S of n minus 2. and then it goes all the way down to S1 and S0. And you have 2, 3, and then you have 0, and then you have other values that aren't 0, and you have like 4 something, and then let's just say this is like 5. So we're going to deal with this is case 1 right here, 0 only in the first column. Then case 2 is the entire row is 0. So that means you got a row of zeros. And so for this case, what you're going to have is the following. It's going to start from S of n. It's going to be S of n minus 1, S of n minus 2, then go all the way down until S of 1, S of 0. And so here, if the entire row is zeros, say this is 2, 3, then you're going to have 1, 2, 3, entire row zeros. And then it's going to be 4 and 5. And so this would be the other case we might encounter, entire row zeros. And so what we're going to do is we're going to examine each of these ones and see how we would approach it. So we're going to look at 2 examples in order to see the 2 cases, one for each. And so let's look at this one. So for this example, determine the stability of the system. And so for the system, we had G of S is equal to 10 all over S to the power of 5 plus 2S to the power 4 plus 3S to the power 3 plus 6S squared plus 5S plus 3. So from here, what we're going to do is, remember the Roth Hertz, we're expecting 5 poles because it's to the power of 5. We're going to make our table. S to the power of 5, S to the power 4, S to the power 3, S power 2, S power 1, and S power 0. Okay, so coefficients are 1, 3, and 5. Coefficients are 2, 6, and 3. Okay, now we're going to do the determinant. When you do determinant here, you're going to get 6 minus 6 over -2, you'll get 0. And then when you do the other one, you're going to get 7 over 2. So this is case 1, right? You have a 0 in the first column, but numbers in the other ones. So what you're going to do here is you're going to replace this with, notice if you multiply by 2, you could actually simplify this. So it would still be 0, and then this would be 7. So you can simplify the row. But then you're going to replace your 0 with epsilon. And so now when we do the determinant of this part, and then you're going to get 6 epsilon minus 14 all over, and then epsilon. And then here you're going to get 3. And so what we're going to do is we're going to simplify this row. We're going to make it multiply everything by epsilon. So this would become 3 epsilon. And then here we're going to get 42 epsilon minus 7 times 14 minus epsilon squared all over, and then 6 epsilon minus 14. And then this would be 3 epsilon. And so what we're going to notice here is basically, are there sign changes? And what you do is you treat epsilon as basically almost 0, like approaching 0. So it can either remain positive, which here it would remain positive, but it's basically acts as 0. So right here, what I mean by that is 1, 2, and then it goes to epsilon. So it's 0, but think of it as approaching 0. So it's still positive, but here it's 0 minus 14. So of course this is negative. So it's going to have a sign change right here. Here we're going to see within our specific one, it's 7 times 14. So this would be 42 epsilon minus epsilon squared. This one, we're going to see another sign change when we go from here to here, this one down here. And so there will be two, and then see how this is still, this will go positive, but then this is 3 epsilon, so we treat this as positive, so there's not another sign change. So there's 2 sign changes. So that means that there's 2 poles on the right-hand plane. And remember, we were expecting 5, so there must be then, as a result, 3 poles on the left-hand plane. So this is an unstable system because there is 2 poles on the right-hand plane. And now that we determined that, how to deal when we have the first column is 0, we're going to look specifically at now the row of zeros. And what is the row of zeros here? Okay, so for an example, it's going to say determine the stability of the system. And we're going to have our system defined as g of s is equal to 10 over s to the power of 5 plus 7s to the power of 4 plus 6s to the power of 3 plus 42s to the power of 2 plus 8s plus 56. Okay, now that we have this entire system, we have to make the Rothford table. So s power 5, s power 4, s power 3, s power 2, s power 1, s power 0. Okay. From this Rothford's criteria, I'm going to fill in my coefficients. I have 1, I have a 6, I have a 8, and then here I have a 7, I have a 42, and a 56. So when we'll notice that this column can't you simplify, divide by 7, so it's 1, 6, and 8. And so this will now become, what we're going to see is when you do it, 6 minus 6 all over -1 is going to be 0. And then when you do this one here, 8 minus 8 all over -1 is 0. And then when you do it here, you're going to get a 0. So you're going to get a row of zeros. Notice that you have a row of zeros. In the row of zeros, notice that the first and the second column were the same when you got that row of zeros. First and second, sorry, row, not column, are the same. And that resulted in a row of zeros. Just take that into account. So what you have to do is you use the auxiliary row. And so this is known as the auxiliary row here. So the auxiliary row right here for the s to the power of 4 is this one right here. We're going to use as our p of s. You're going to make your p of s from it. So it's going to be s to the power of 4 because this is s to the power of 4. And remember, this is to the power of 2 plus 6 s power of 2 plus 8. You take the derivative of the auxiliary row. So the derivative p prime of s is going to equal 4s to the power 3 plus 12s, and then derivative constant 0. And then now that we have that, we're going to then fill in this one with that auxiliary. So it's 4s to the power 3, so coefficients 4. Then this one would be our 12. And using that, we're going to get the result. We're going to now have 12 minus 24, which is -12, divided by -4, which we're going to get 3. Then we'll get 8, and then we're going to get 1/3 here, and then 8. And so what we noticed here with our auxiliary row, now we have to determine the stability of the system. So this will be a little complicated. So in order to determine the stability of the system, what we have to do here is we notice specifically that before the auxiliary row, we had one row here. So this would be one stable pole. because before the auxiliary row, there was one row. So this is stable. And then we notice within here, how many sign changes did we have? We had no sign changes. And so now what we need to know is if we had no sign changes, then there's no unstable poles. And so the rest of the poles basically are going to fall along the J omega axis by process of elimination. So if we have one stable pole, we're going to have one stable. There's no sign changes, so there's 0 unstable. And so the only possibility that's left is marginally stable. So there must be 4 marginally stable poles. Okay. Now that we got that, I think that is a pretty good example. The reason being is because you have to look at the poles before the auxiliary row. That determines your stable ones. How many rows you had before the auxiliary row, that's how many stable poles. If you did have a sign change, remember that the sign change, there is a stable pole for every sign change you have, because that makes, if you have a sign change, there's an unstable pole. And what you're going to see is then due to the symmetry about the origin, then there has to be a stable pole to follow that unstable pole. And then by process of elimination, the rest of the poles are marginally stable. And so that is a big thing to take into account when you're looking here at the row of zeros. And so those are the two possibilities you can have. And that will conclude the lecture on stability.